Okay, can you hear me? Okay, yeah. All right, so it's 10 after, so we're gonna get started. So thank you all for attending day 4 of our Noble Lecture Series. If you have attended the previous lectures, you've heard about Dr. Anne-Marie's impressive career. Her research has predominantly focused on the development, operations, and validation of satellite instruments. Her current work at the National Institute of Standards and Technology focuses on connecting satellite measurements of carbon dioxide and methane to international standards and refining data to effectively meet the needs of users, including governments and industry professionals. As Dr. Eldering mentioned in her talk yesterday, the validation of these satellite instruments, which typically requires ground-based measurements, is crucial for properly interpreting their data. These ground-based measurements will be the focus of today's talk, titled The Cutting Edge of Ground-Based Measurements, Frequency Combs, and Cavity Ring-Down Spectrometers. Please join me in welcoming Dr. Anne-Marie Eldering.
All right, thank you so much. How's our volume in the back? Good. All right, thank you again for having me here in Toronto. And the week is getting more and more fun as the faces become familiar. I meet with people and actually know who's who, so really enjoying this. So today, a few disclaimers I want to make before we get started. I'm reaching the edges of my knowledge here, so I did a lot of reading to prepare this talk. People might in the audience may know more than me about these topics, so my apologies if I mess anything up. I'm going to talk a little bit about Fourier transform spectrometers too, and my apologies in advance to Kim and Deborah and other experts, because I'll probably misrepresent or simplify some things on that front. But the point is to talk to you a little bit about some exciting new measurement techniques, and this also has links to NIST. So this kind of helped me learn what my colleagues at NIST were doing as I prepared to talk to you about measurements. And I changed the title a little bit, so it's frequency combs, yes, but it's going to be laser heterodyne radiometers rather than cavity ring-down spectrometers. You won't really care. And also take this as a journey of exploration. Bring out your curiosity. There is no exam on this. You will not be tested. Don't sweat it. Just try to hang on as I wander through some new territory here and see if some of this stuff is interesting or exciting. And hopefully we won't lose you too fast in this material. So I'm going to talk a little bit about Fourier transform spectrometers. And then I want to introduce femtosecond lasers and mode lock lasers, which is something I had to learn all about to really understand any of this. Frequency combs and laser heterodynes, and a little example of what people are doing with it today. So we're going to cover a lot of stuff, not in much detail, but just kind of take a through journey of some new technology and ways people are trying to use it. So this all starts with SI units. Who loves SI units and standards? Whew, okay. So working at NIST, you have to say you love SI units. So that was part of my job, you know, application. Yes, I think the units are great. And that's what they focus on. And so, you know, in instrumentation in our work, we're always trying to advance things, make them more accurate, more affordable, more precise. And at NIST, there's a special focus on standards and how they evolve, and the evolution of standards pushes the evolution of the technology as well. So the work, I'll show you how these pieces kind of come together. And then at NIST, there's scientists working on frequency combs, and some work on laser heterodyne. And so I wanted to highlight some of that stuff in this talk. So this is a meter, right? This is what standards used to look like. We made a meter in the stone and everyone referenced back to it, but it doesn't work all that well. And there's been a change in philosophy now. We don't want, do we need to change volume? Oh, shoot. We did that already. I just forgot when I did something else. Okay, sorry. We gotta do a couple more things here. Do that, do that. Okay, does that look good in the outside world? All right, let's see if my clicker still works. No. Okay. All right, so where were we? So standards. This used to be the standard for a meter, right? We would have a physical thing that was a meter or a kilogram, and that's how we knew what those were. That doesn't meet our requirements any longer, and there's a big effort to bring standards down to like fundamental quantities. And so in doing that, for example, the second was redefined in relationship to the cesium molecule and its vibration. So then there can be no argument. If everybody's instrumentation works properly, everyone will know what the second is, and it will be the same everywhere all the time. And similarly, the meter then gets related to that second. So you have these units that are being tied to fundamental constants. But when you see things like, for this second, we need, 9,192,000, et cetera, oscillations. So how are you going to count that and know that that's what you got? So you have to have more and more precise measurements to be able to do these standard-based or fundamentally based standards. So there's a lot of need in the community of the standards world for better instrumentation as they try to make this transformation. And so this ties back to frequency combs. So this is a picture of the 2005 Nobel Prize winners. And one of those was a guy who was actually at the NIST at the facility I'm now at. And they built these optical frequency combs. And they did this because they were trying to build an atomic clock and get a really precise measurement of time. But you needed more precision than they could manage. And there was this way, which I don't fully understand, about how you basically have frequency multiplication chains, and there's methods to try to relate something, say, in the gigahertz range to the terahertz range, but it's super complicated, and you could only get like 2 measurements a year out of these hyper complicated massive things. So it really didn't meet their needs. And they went through the work and figure out how to develop these frequency combs, which really helped them get this atomic clock and precision that they were after. So this was driven by standards and atomic clocks, but then other people have adopted it to all sorts of other pieces of work. So what I wanted to just highlight in this one, right, we have a lot of experience in instrumentation in your community. The Fourier transform spectrometers have been at the heart of a lot of the work. They're great because they have this really big band pass, and you can measure a lot of molecules all at the same time. As you could see probably through my other talks at the Jet Propulsion Lab, we also do a lot of work with grading spectrometers, which have a lot of benefit. There's no moving mirrors in your grading spectrometer, which has some advantage to it, but the band pass isn't quite the same. So the FTIR has become favored for a lot of the work we do, but there's challenges, right? You have detector nonlinearity, modulation efficiencies, alignments, and so on. So people are always searching for some other technologies, and maybe they can find an instrument that has all the positives and not so many negatives. So that's kind of, I think, the mindset we see in some of the stuff I'm going to talk about today, is just this search for always looking for new techniques and things we could use perhaps in the ground-based measurements. And again, in that conversation about plumes and methane validation, we think that some of the approaches to date don't have all the qualities we need for validating these plumes that have a variety of shapes. They're transitory, they're small. So there's groups that are advocating for new ground-based measurements that might be appropriate for plume measurements. And you'll see that in some of my example applications, that they're taking them out in the field and trying to demonstrate what they can do. So that's just kind of context setting of some of the new techniques. All right, so here we're going to take a little bit turn and just get everybody on the same base, at least with my framework around Fourier transform spectrometers, because this idea of constructive and destructive interference comes back in some of the other topics we want to talk about. Right, so the idea is that you have waves that interact, and at certain relationships between the waves, you'll get this sort of enhancement or constructive interactions, and then you can have destructive interactions where you're basically canceling out each other. And so that's kind of at the heart of what happens in the Fourier transform spectrometry. And another thing to think about, or again, concepts, and I am simplifying things, I will admit, is that you have relationships between frequency domains and time domains, and Fourier transform spectrometers are moving things between those domains. And when you do the reverse of the transform, you can go back. So there's always frequency and time relate to one another. You can, if done properly, you can gather data through one transform and reverse it through the other. So just again, a concept to think about, and you'll hear that in some other context. And a classic building of a Fourier transform spectrometer is this Michelson design, where you have light that's coming into a beam splitter, and some reflects to a fixed mirror and some reflects to a mirror that moves. So this translates back and forth, and you shift yourself through that constructive, destructive interference patterns. So you get an interference pattern of the light that's happening as you move the mirror back and forth. So that's kind of the fundamental, a typical implementation of a Fourier transform spectrometer, that you are able to do that interference work. And again, you'll see on my next slide that the movement is recorded in time as the mirror distance changes. And so that's how you go from the frequency of light to a time domain as you sample through. And you get an interferogram. So this is a recording of how did that light interfere with it's the beam split portion as a function of mirror position or time. And this is also typical that the signal covers a wide range, dynamic range, especially in the center of the interferogram. You often have a very large signal and small signals out here. And as you'll see, that can be challenging because you need to be able to record information being sensitive to both the large signals and the small signals. So that's what an interferogram is. And then you can invert that and get back to a spectra. And just think the key thing I want you to think about here is optical path difference is a phrase that we use, and that's in centimeters. How far apart are those mirrors in centimeters? You do an inverse of it, and then you get inverse centimeters or wave numbers. So that's how these things kind of can be connected. And we needed an equation today, so I put down a Fourier transform equation. So we have these Fourier transform spectrometers. Have you all touched one or seen one through your physics classes? Mostly, not our global modelers. Okay, but I'm sure Kim and Deborah and the other students will share their FTIR if you want to take a look. So why do we love FTIRs? Well, as I mentioned, you can get big band passes. You can see a lot of wavelengths of light. And then if we look at this optical path difference thing, the spectral resolution is the inverse of the optical path difference. And if you have a 45 centimeter optical path difference, which is what is typical in some of the bigger ground instruments, you can separate wavelengths in the 0.02 wave number. And that's a really wonderful resolution. You can start to see details with that kind of a resolution. So that's a strength of its FTI. And then there's other things people will talk to you about, how the light is collected and the way the noise is, et cetera, et cetera. There's many advantages to Fourier transform spectrometers, and the reason that they're used in a lot of different settings. But then, of course, not everything is beautiful. If you think about the line shape, like how does the instrument imprint itself on the data I collect? Theoretically, it should be kind of like a rectangular function. And that would make it easy to take it back out because you know exactly what it looks like. But this is a figure I stole from Boone and Bernath about the ACE-FTS, showing some of the data that they have from their analysis about what the true modulation efficiency looks like, and that there is dependence on the optical path difference and is not all beautiful. So there's, as you know, not surprising, the theory and the actual implementation are a bit different. And so you have to really understand that if you're going to use the data from your FTIR. And everybody's got that issue. A grading spectrometer has an instrument line shape as well. And these are some figures for the OCO instrument where we characterized our line shape before we launched. We launch it, but in flight, it's performing a little bit different, and people have ideas about how they can suss out what's really happening. And so he's used different representations of the line shapes to try to optimize what is used in our data analysis. So it's an issue really that I think everybody has to grapple with the line shapes. So, you know, some of the things we love about FTS, wide spectral coverage, you can go out and buy one if you have a big pocket of money. You can just go call a commercial company and get one. You don't have to build it in the lab yourself. There are moving parts that can make it a little bit tough when you go to space, because if they don't move like they're supposed to, which is what happened to TESS, our emission spectrometer that we sent up to do chemistry. If I remember the story right, the material they put in there for lubrication wasn't quite what it should have been. And so after a few years, it didn't move that smooth. And we actually had evidence that the Teflon belt it was moving on started shredding, and it all became a little bit ugly. But there's been better designs now for your spaceborne instruments, so didn't make that mistake twice. And one of the things the standards people will harp on is you do not know your frequency scale. Absolutely, you have to calibrate that with some other measurements. So there's some things we might try to figure out, can we do it a little bit better? And so what I'm going to do is talk about some new instrumentation. And the other idea I want to impress is it's not like somebody went out there and said, oh, I have this brand new way, I'm going to make measurements. What really happens is they go, well, I have a Michelson interferometer, but maybe I can improve this aspect of it. Or the detectors are problematic, let's use this technology. So you sort of see a reinvention of methods with improvements in different aspects of the measurements. And so I'm going to now spend a little bit of time talking to you about lasers and then try to relate that to these different measurement techniques. So lasers, I'll describe in the next 3 pages a little bit of detail, but you have some sort of material, you excite molecules. As they relax, they give off energy, it bounces around in a cavity, and then you bring some of that light out at the end. And as you'll see in the slides that follow, how fast these pulses and how short they are is a key characteristic and has a lot of importance to what you can do with the lasers. So very fast, femtosecond, 10 to the minus 15 seconds was a key breakthrough in lasers that led to a lot of the work that I'm going to talk about here. So these are things I didn't know before I told Dylan I'd come and give you a talk. So walk with me through a little learning. So the gain bandwidth of a laser has to do with how many frequency of light can I get through my laser system. And the material that you're using determines this property of it. And so a couple of examples is a helium neon laser has a wavelength of about 622 nanometers, but the bandwidth is only 0.002 nanometers, so it's very narrow. In contrast, TI, help me out somebody. Titanium sapphire is like, really titanium? I think it's titanium in my bicycle frames, but okay. Titanium sapphire laser has a bandwidth of 128 terahertz or 300 nanometers centered at 800. So huge contrast in the gain bandwidth of titanium sapphire versus a helium neon laser. Okay, so materials change that, and it's really big for titanium sapphire, small for helium neon. So another important aspect is the cavity of that laser. I said the light bounces around and that cavity determines behaviors of it. And what we want to say here is you end up with a standing wave in that cavity. So the length of the cavity and how many multitudes of the wavelengths fit is a key parameter. And this is not usually 4 or 5, this is 10 to the 5th, 10 to the 6th frequencies can resonate in there. So a typical dimension, you might have a 30 centimeter laser cavity. And for those 2 things I was telling you about, the 2 different lasers, for the helium neon, that means you can get about 3 longitudinal modes in that cavity. For the titanium sapphire, it's 250,000. And this is related to the, find my number here. Right, is really related to the bandwidth of those 2 things. So big bandwidth, a lot of modes can be there in the cavity. So that's why the titanium sapphire is very different from the heme. Okay, now this is going to connect, I promise you. So in this mode, then you have this mode locking, or how are all those standing waves in the cavity relating to each other, and sometimes they interact in such that you get an enhancement, and that's the light that suddenly escapes out the end and gives you the pulse duration of the laser. So the pulse duration relates to the number of modes of the frequency. And remember, the Heme and the sapphire are really different from each other. And when it all boils down to it, you've got like a Heme laser has that narrow bandwidth, a small number of frequencies, and then a pulse duration, which is long. It's 300 picoseconds, whereas a titanium sapphire, we said it had 250,000 modes in it, and that drives it to have a 3 femtosecond pulse duration. So lots of modes, super short pulse duration, not so many modes, longer duration. So this is where you get to femtosecond. For a 30 centimeter cavity laser, you can have femtosecond pulses with something like the titanium sapphire and these modes. So we taught, there's how fast does that pulse come out? How long is its duration? And then how many modes is it supporting? And so this is going to be the heart of the frequency comb. If I want to send some light out and do work with it, if I just have 3 modes, it's not going to be like powerful in interrogating something. If I can send out 250,000 modes with this very small separation, you can think of that as like a comb of light with 250,000 fingers, and you're going to say send that through a sample and see how it changed. It suddenly gives you a lot more power to try to investigate something with this laser light output. And again, the femtosecond provides enough modes that this now starts to become powerful, and you'll see how this feeds into a frequency comb. So have I completely lost you, or you roughly have this idea? New types of lasers, new ways of setting up a stream of light that's going to be useful for things I want to do. All right. Whew. So this is a paper that has a great overview of this kind of technology, with Hansch is one of those Nobel Prize winners, and then Nathalie Piquet is a collaborator. So I stole a lot of figures from that paper. So this is the general idea that you use a laser like that femtosecond laser, generate a frequency comb of light, and I'll get down to some specifics in a bit. Send it through a sample and measure it at the other end, and you basically see the absorption feature imprinted on top of that frequency comb. That's frequency comb at the basic. So what do people do with this crazy new thing? Well, we try to make measurements of gases. One of the things you'll see in here is it doesn't have a huge bandwidth, especially when you compare it to Fourier transform spectrometers. In wave number space, right? Your spectrometer can cover thousands of wave numbers. Frequency comb is a few hundred. But then in the resolution, I said we were so excited with measurements of 0.02 wave numbers. Well, the frequency comb spacing is 0.067 wave numbers. So more than an order of magnitude reduced in that spacing of the frequency. So that's probably the biggest step forward with this. And frequency knowledge is included. So you know exactly what frequency those wavelengths of light are. You no longer have to calibrate your frequency scale. So advantages and disadvantages in the technology. So people do all sorts of things, and I'm just going to show you a few examples here. So you might use that frequency comb as your light source, put it through a sample, and then interrogate it with an FTIR on the other end. So there, instead of using incandescent bulb, you're using a frequency comb, but you still have frequency knowledge. And as I'll try to describe later, you know a lot about that input light, and that will have some advantages. So if people use it in FTIR measurement systems, and this is an example of a spectra that comes out from that type of work now. And my units are going to be all over the map: wave numbers, nanometers, microns. My apologies. That's what happens when you steal people's stuff. So here's 1.6 nanometer CO2 band, another CO2 band. So this is the full spectra that measured with the frequency comb, and then you can go see a few details that they pulled out. So they can interrogate a lot with these kind of frequency combs and get a lot of detail about the spectra. And often now what we see people doing is they basically use the two combs as kind of a way of doing interferometry. So you have one frequency comb and then you build another comb at a slightly shifted spectra or slightly shifted frequency. And then that has that interference behavior like we talked about with the FTIR. And the folks who wrote this paper will argue that you can do that, but you don't have to worry about the moving part and how that sets what you can do with the resolution of things. And so you can get down to really, really high resolutions with this kind of technology. And I think I have got a little example of an absorption spectrum measured with this technique. So the dual comb is one. DCS, dual comb spectrometry, is something you'll see in a lot of the applications in this technology. And this is an example maybe less related to the science that we do, but it was explainable. So they took a dual comb frequency spectrometer and measure solar light. And this is just the magnesium ion lines that were measured with that. And so you can see here his fit and then his actual measurements. And again, a lot of this work is reported in hertz, which I have a hard time relating to other things you might know, but you get the idea that this is a single absorption line captured with many pieces of information throughout the line. And of course, from the standards world, he was super excited because he's added one more digit in the precision of where they know where that line is, and his uncertainty is lower than anybody else's is. So they're really, you can see, okay, you can go to the lab and very, very precisely locate lines and absorption features to another order of magnitude better than we used to have. And this is an example where they've, again, in a laboratory made a dual comb frequency spectra, more in a region that we might care about. So this is overall what that measurement looks like. So the frequency comb has a shape, kind of a baseline that they have to account for. If you zoom in, each of those are a comb line, and then this is an absorption feature that's been imprinted on it. And this is in gory detail of each of those comb lines. So they're not a delta function, right? You don't go from 0 to something. It still has some structure around it. But these guys will argue that that is known and characterizable, so they can account for it when they try to analyze the data. And this is where they've transformed this into an absorption spectra and then done a fit with it to determine characteristics of the absorption features. So again, you see that each line is got multiple measurements within it as they try to characterize the absorption behaviors. So the dual comb has definitely got some power in it. And what we see at NIST is folks are using it in their laboratory spectroscopy, which I think is a fantastic application for this. So there's people at NIST who do fundamental spectroscopy. What's the behavior of the CO2 molecules, the O2 molecules, and others, which feeds directly into data interpretation like what we do at TCON. And this one, he happens to use a cavity ring down, which in the broadest sense is you excite a molecule and then let it decay. And you have, again, a cylinder with highly reflective mirrors, so the light's bouncing through that. And the decay time is informing you about the fundamental characteristics of the molecule. So that's been a spectroscopy technique that people have used now for some time, but then he adds this frequency comb, so he has the absolute frequency information and very high spectral resolution information to be extracted. And this again is an example of what he actually gets out of the system. So he's measuring the oxygen lines. And I thought this was really interesting. On the upper left is the oxygen line. He's measured at a number of different pressures. So you see pressure broadening effects happening clearly, where your lowest pressure is here at the bottom, and then the highest pressure is at the top. And then they fit that data with different line shape representations. So the other day I threw out how Voigt profile is kind of a basic, easy to calculate broadening representation, but the more information we get through these laboratory experiments, the more we realize that the Voigt profile does not do what we need, right? These are the residuals when you fit it with a Voigt. So actually, he ends up fitting it with their speed dependence Voigt profile here, which is still not perfect. And then there's this speed dependent Nelkin-Gattack profile with some adjustment to it. And I'm sure Deborah will have a sidebar if you buy her coffee. And that's actually has a very uniform residual. So these new interrogation techniques reveal details that we weren't seeing before and force us to try to come up with even better representations of how the molecules are interacting and how the pressure broadening is happening. So again, a great laboratory example of why frequency comb is useful. But of course, you give a scientist a tool and they'll just do all sorts of things with it. And here, the group at the NIST in Boulder and the University of Colorado have been on the forefront with taking frequency combs out in the field and trying to do experiments. And I'm just going to touch on a few things that they've done, but I found examples where they looked at vehicle emissions, agricultural emissions, as well as plumes and methane leaks. And so what I want to do is describe what they did and then just ask a few questions like, is this useful? What's the benefit of this? What's not really working great about these systems? And this paper that Eleanor Waxman wrote, I thought was one of the more complete perspectives on the work. She wasn't just selling what she did, but she was kind of thinking of what was beneficial about it and what didn't really work. You know, and talking about you can measure over 2 kilometer path lengths with these systems, which is really useful for field work. You get all the measurements at one measurement captures all wavelengths, and Lawson and I were talking about turbulence in the atmosphere. So that's one advantage, that it's a quicker integration and you may be immune to some of these effects. But like I was saying, if you had a pocket of money, you can get an FTS. If you have a pocket of money, you cannot buy a dual clone Fourier transform spectrometer system. You got to go talk to some people, buy parts and put it together in the lab. So we don't have turnkey systems for this yet. So this is really experimental development type work. And what they did out here in Boulder was they set up their dual comb spectrometer. You have to have a retroreflector to bring the light back to you. This particular paper, they were comparing 2 systems to learn about their performance and some of the details, but I'm just going to highlight overall the results. So they had their instrumentation here in a reflector and get this open air path. Eye safe laser, so they don't have to worry about frying people's heads if they walk through their beam. And I will share these slides if anybody ever wants to look at more details. So just getting to the results pretty quickly, this is what that spectra looked like that they collected through the dual comb system. And then they have to, again, account for the comb baseline. And then you zoom in a bit and you see this spectra. Again, these are all frequency combs with the little absorption features imprinted on them. And if you look down at even more detail, this is the one comb, the next comb, and these are spaced at that 0067 wave number spacing. So they were able to do these open air measurements and then convert that into an absorption spectra. So we see our carbon dioxide features here. And then if you zoom in, this is the details of the absorption line. So they do interrogate this with a great deal of detail. And it's a beautiful absorption spectra. But then they want to know CO2, so they got to go through the same painful process that everybody else does and say, well, what do I think the line absorption characteristics are? How do I invert that back into a concentration? And she even talks about in this paper of how there's all sorts of sources of error. She provided a nice little table and really interesting, you know, correcting for water is important, 0.4 part per million in our CO2. Temperature in homogeneities. But look at this, the spectral database itself is the biggest driver of error, and 1 to 2% for carbon dioxide. That's huge. We don't like that. So they suffer the same problems that we do, that they have to interpret this data. And it seems like you a little bit have lab spectroscopists are using this technology. You would think our spectral databases should be getting better and better, and then we could use them in our interpretation, but I don't think those things are moving together exactly hand in hand. And it's, you know, similar thing for methane, that the spectral database seems to be her biggest source of error. But we see more people doing work. This is from the NIST website, one of their advertisements for looking at plumes through dual plume spectroscopy tools. And another experiment that the NIST Boulder group did, where they actually did a controlled release experiment, kind of like we were talking about yesterday, set out their spectrometer. These are oil and gas pads, and then they actually purposely had a little bit of methane leaking out. So I thought, oh, cool, this is kind of like what we've seen before. But what's amazing here is they've got, with a 2-kilometer path length, 2-minute averaging time, they have this comparison, and look at the emission rates. These are grams per minute. We were talking about kilograms per hour yesterday, and we were talking about hundreds to thousands of kilograms per hour. 1 kilogram per hour would be 16. It would already be off this chart. So these are tiny, tiny amounts. And they're doing this to support an activity of ARPA-E, which is a funding agency in the US government that's trying to get technologies ready to find leaky methane in old oil fields. And they want to try to get down to 1.8 grams per minute. So that's why these folks are working. So they're working in a different realm than we are. But it does seem that there's some power in this dual cone for finding the plumes. They've got to do the same interpretation though, right? You have this, you can set out a little network and be looking around you through 2-kilometer paths, but you still have to do some sort of inversion to get an estimate of the emissions rate. And actually for this figure, they, I think, aggregated to 30-minute data to try to do the inversion. So there's still this issue of the inversion, an issue of the line strength. There's a lot you have to do with that dual cone spectrometry data once you gather it to really get what you're after. So I don't know that it's a slam dunk, but it's definitely in maybe another tool that we could put in our toolbox. And laser heterodyne radiometry is going to kind of fall into that same box. So it's a method that's a column measurement. Need to look at the sun. It's got a super narrow band path with exceptional spectral resolution. So we'll just skim through this briefly to give you a little bit of a concept of things. So the idea is that you have some light source and then you introduce light that's at a slightly different frequency and mix them, and you get 2 streams of light out, which are difference, sort of the difference and the addition. And if you set that up in the right way, you can use it to interrogate different band passes of light. And I think I noted on here, it's a Canadian idea from a Canadian inventor. And this has been around for quite some time, but in a different context. So some of the papers I found were from the planetary community, and they were trying to look at behaviors of the planet. And the thing that they were really highlighting is that the signal to noise that they could get was impressive for all the techniques that they had available to them. So when they wanted to look at Saturn or Titan, Uranus, Neptune, this methodology gave them advantages they didn't have otherwise. And this was one of the papers in 1983 where they looked at Mars, and the little dots are the samples that they have as they interrogate just this one line to try to learn about the atmosphere of Mars. So this is the kind of work I was finding from the 80s with this laser heterodyne technology. And then of course, as electronics have advanced and lasers have advanced, there's new versions of these things. And the one I want to highlight is what Emily Wilson, who's at Goddard Space Flight Center and NASA lab, has been working with the telecom lasers, or the 1.55 micron lasers, to try to do things related to atmospheric science. So you can see this idea. She's going to look at the sun using fiber optics to bring her signal in, and then she has a local oscillator that she couples and gets that heterodyne signal out of it. And this is an example of a measurement she's made of one absorption line. This is for for carbon dioxide. So not quite the spectral resolution you're seeing with the frequency cones, but you can still interrogate a line with this. And she's managed to make this a really small system. So they were trying to do work, I think, up in Alaska, and they couldn't drive where they were going. They needed to walk in with the equipment. And so that put some limitations on what they were going to carry. So she found a way to really build a little small system. This is what their sun tracking looks like. And then they kind of got the Pelican case with it. And they did do some work where they came and measured next to TCON instruments as they tried to understand and learn about the system that they have. And this is just some examples of what they did with a test up on Mauna Loa, where they, again, were measuring methane and carbon dioxide. And you can see if you read her papers, as the time went on, the system improved, the integration times reduced, the noises of the system reduced. So she's, again, able to get some really detailed data, but you're generally measuring 1 or 2 absorption lines with this strategy. Which in my mind, there's a lot of downsides to only having 1 or 2 lines, because you can never learn about baselines. A lot of what we've done with the carbon dioxide, you want strongly absorbing and weakly absorbing. So you're seeing all the layers of the atmosphere, different approach with these. And she did do something cool. She actually built a CubeSat size one of these systems. So they were going to get it in space and do occultation measurements through the atmosphere. But unfortunately, in the launching of the CubeSat, it got sent off with a lot more spin than they were expecting. And they didn't have it in a way that they could stabilize themselves. And they basically lost all their battery power and it was toast. So they didn't have success with that experiment, but at least showed that you could build laser heterodyne radiometers that are CubeSat size. So back to that conversation we were having of, do you build 300 of them for not much money and learn something that way? Although I did work on occultation data in the past, and Kaylee and I have talked about that. Your sampling is limited with occultation strategy. So again, I don't know where that's going to take the laser heterodynes. So that was a little sidebar on what Emily Wilson's doing. And then of course, again, the people at NIST are crazy. So they've taken a frequency comb and a laser heterodyne radiometer and married them together. And why would you do that? Well, he's trying to interrogate elemental lines again. And this is an iron line that they interrogated. And the 2 things I want you to take home from this is that he says that he has fractional precision of 1/4000th of a line width. So in that, just that single line he's measuring, there's an incredible amount of information. And then what he's trying to show here is that you can really predict the performance of the system. There's not a lot of unknown unknowns in here. If you understand the efficiencies of your detectors and the throughputs of your fibers, et cetera, you really know what you're going to get out of here. And in reading this literature, it seems to me like they have fewer issues with instrument line shapes, and some of the artifacts, because of this technology, is closer to Dirac functions. And some of that's proven out. Certainly for the laboratory work, you can see, you can, again, find the frequency of the magnesium line order of magnitude better than you knew. For the field work, not so sure about it. They did take that kind of instrumentation out into the field to measure carbon dioxide. And so here's one beautiful line they measured with a 2-hour integration. Is that what I want to do my next field experiment with? Not so sure. Maybe a little bit of a hammer looking for a nail here. But they showed they could do it. And there are groups I found were building these portable laser frequency comb laser heterodyne spectrometers. And this was interesting. I only found this kind of stuff. This one was from a conference in 2022. And this also is from conference work. So it's sort of really in rapid development because it's in conferences, not yet published. But I think they're convinced, again, that this could be useful to have as a field experiment. You bring it out and do measurements of the atmosphere with these systems. So demonstrating they can make measurements of carbon dioxide lines with the system. So, we have this laser heterodyne. You can't buy these either. I think one of the reports was about $10,000 of parts and knowledge. You can put those things together. It does have absolute frequency calibration if you marry it with a frequency comb, but you're only really seeing a single line. So we got to think about what's the usefulness and application of these. Is it going to inform us about something? So we're willing to take that trade-off about the spectral information. And for the frequency combs, certainly for the laboratory work, I'm absolutely sold that these are great systems for lab spectroscopists to have. Investigating things tied to an absolute frequency reference. I was amazed after I read and reread that Alden paper that she set that out in the field and got gram per minute leak rates. So there's probably some utility in some settings for these things. But they still suffer from this interpretation problem. You can have the most beautiful spectra in the world, but you measured over 2 kilometers. Do you know how much water vapor is there? What's the turbulence? What's the inhomogeneity? I think there's still challenges in interpretation. So it'll be interesting to see how these things evolve in the future and what people manage to do with them. That is really informative. So I'm going to leave it there. Hopefully you had fun on our journey today through lasers and frequency combs and strange things that people are doing. Definitely, new technology on the scene. How we're going to find utility in it, I don't think it's completely clear yet. I do kind of imagine, a backpack system that's not costing an arm and a leg would have some place and field measurements that we want to do. And maybe you'll even figure out that it fits in some of the research projects that people have here. So it's kind of it's a fun time, right? We've got satellites, we've got new technology being built. We don't know how people are going to put it all together. So it's kind of a neat time to be seeing the field evolve. And thanks for taking the journey with me today. Happy to answer some questions because I'm sure I left a few of them. Thank you.